So now that I started with some of the fun stuff, let's move to some of the boring stuff. Nah, it's not that bad really, but we do need some terminology and so on. So this is what we're going to introduce for application security. And it will help us know what we're talking about later, even if informally I've already used some of these terms. So these are general terms used in software engineering. Now, I'm not a software engineer, but even I am using these terms because they allow you to clearly specify what you mean. So let's start from this starting point. From now on, a fault is an incorrect step, process, or data definition in a program. From my perspective, a fault is typically a bug. That is, the programmer made a mistake and now there is something wrong in the program, which is a fault. Faults can also be hardware faults. For example, if a cosmic ray changes a bit in memory. Now an error. An error is the difference between a computed, observed, or measured value, or condition, and the true, specified, or theoretically correct value or condition. Now this is a long-winded way to say there is something unexpected in the program's state, where state refers to the memory and registers that are currently active. Right, so some of the data is now wrong. So to distinguish the fault and the error, the fault is an issue with the program and the error is an issue with the program's state. Now finally, an error can result in a failure. Right, so a failure is the inability of a system or component to perform its required function within the specified performance requirements. So, for example, the program crashes. When the program crashes, it's no longer useful. It's no longer able to perform its job. Right? So a fault is made when writing the program. It can result in an error at runtime, and this error in turn may or may not result in failure. And only by the time we get to the failure do we actually see that something is wrong. So now we get to the security specific terminology, namely vulnerabilities. What is a vulnerability? Well, a vulnerability is a fault, and in particular, one that has a security impact. So security impact essentially means that a potential attacker is able to threaten one of the CIA properties, namely confidentiality, integrity, and availability. So any fault that allows an attacker to do this is called a vulnerability. And a program containing vulnerabilities is called vulnerable. Now, in practice, almost all software out there is vulnerable because it's impossible to write a program without making mistakes. So in this course, we mostly consider software faults. So this is the case where a programmer makes a mistake or a bug in the program. Now this can be contrasted against hardware faults, which include, for example, bit flips due to cosmic rays. However, also hardware faults can definitely be vulnerabilities. Even here at the appsec group, we do a lot of research into hardware vulnerabilities. And you may have heard about Spectre and Meltdown, or perhaps even the Riddle vulnerability, which was found by us. So there are in fact many hardware vulnerabilities out there, and they're interesting to exploit because you can do this even if the software is completely flawless. But for now, let's focus primarily on bugs that are introduce vulnerabilities. So a question for you. What is the vulnerability in the example program? Please pause the playback if you want to think about the answer. Well, the answer is the missing size check before string copy. So string copy string copy will copy however many bytes it is passed, but string copy itself does not check the size of the destination buffer. But we can do this manually. We could verify that there's enough space for the data to be written and return an error code otherwise, or do something that prevents us from overwriting the return address. Now, this is where the fun starts. Exploits. Hackers love to do exploitation. Now, what is exploiting a program? It means passing an input that triggers a vulnerability in a vulnerable program, right? So this particular input is also known itself as an exploit. So we pass an exploit to a vulnerable program to exploit it. Now this compromises the program by introducing an error in the program state. So at this point, something is wrong in the program because of what the attacker did. Well, for the example program, what would be valid exploits? Again, please pause playback if you want to think about the answer. The answer is any argument of a length greater than 15. Now you might wonder, we had a 16-byte buffer, so why is the threshold not 16? Well, the reason is simple. Every string ends with a null terminator, and it also needs space. So if we write a string of 16 bytes, the null terminator ends up in the next memory location, which is no good and could be exploitable and could be used in some cases for an attacker to gain control over the program. So in this case, what error does the exploit introduce in the program state? Again, feel free to pause playback. So the error is corruption of the return address and or the frame pointer. Right? In this case, we sent an exploit that corrupts both. So after overflowing the buffer, the values stored on the stack are no longer correct. And this, in the software engineering sense, is an error. Now exploits tend to have some impact. Otherwise, why would attackers even bother looking for exploits? So typically there's two kinds of impacts that you might strive for. One is denial of service, which means that you're interrupting availability. So for example, you might target a web server, causing it to constantly crash, and as a consequence, the web server is no longer available for people who want to use it. Now the second, which is the one that typically in application security, it's the only one we care about, is privilege escalation. So this means we break confidentiality by leaking some secret data, or we violate integrity by modifying some data that we're not supposed to modify. Again, typically we only care about privilege escalation, but there are definitely special cases where this is not valid. So for example, think about a nuclear power plant. Think about other critical infrastructure. Think about pretty much any industrial control system. If you crash the system, the damage might be catastrophic. However, for a simple program that has no ties to external hardware that threatens lives or is critical for things to function, in these typical cases, a program can simply be restarted after it crashes. And in this case, denial of service doesn't matter too much. So we care primarily about privilege escalation. Now, for the example program, what would the impact be? Again, take some time to think about it. So the answer is, it really depends. It depends on the context. How is this program used? So if this is simply a program you execute in your own shell, it doesn't have any privileges that you yourself don't already have. In this case, there is no impact. We can fiddle around with the program. We can practice exploits, but we cannot gain control over something that we had no control over before. However, if we assume this was running inside a web server, then we might be able to get into the web server, even if we had no access before. Then we can actually get privilege escalation. We can, as an attacker, be able to do something that we weren't supposed to do. So in a general case, what can an attacker do with an attack like this? So the attacker can point the return address to code that does whatever actions the programmer wants to do. If we control the return address, we decide where the program continues. Now this could be code injected by the attacker themselves. So the programmer could find a way to put code into the program and then run it. Can you think of a way to inject code in this particular program? Well, the answer is the name. So you could put a name that has code inside. And if you know where it is, you could write a return pointer pointing back to this code. And then second, you might also be able to exploit code already in the program. if for whatever reason you cannot execute the code you injected. Why, you ask, would you not be able to do that? We'll discuss this later as parts of the defenses. Now, this is only interesting if we can perform these actions on a system that the attacker is not allowed to execute on. So for example, a web server, or on behalf of another user. So let's say we have shell access to a system, then if we can execute a program, it's not in itself interesting, but if we can execute a program on someone else's behalf, that might be interesting, especially if the other user has more access rights or different access rights. We could access the other user's files, for example, or if the user is root, we basically gain complete control over the system. Now, what can a defender do? How can you prevent attackers from breaking into your program or your system like this? Well, the best options are the following. First, never introduce any bugs. Now, this is very unlikely. We're after all human, and humans do make mistakes. And mistakes are super easy to make. Even if this one looked completely lame, you'll find yourself making these kinds of mistakes over and over again. And in many cases, you don't even notice. Even though it results in undefined behavior, typically the behavior is as you expected. So they're not easy to spot, but they are easy to make, these bugs. Well, a second option is to use a safe language, right? I was already saying C and C++ assume that you are a star programmer, that you know exactly what you're doing and that you're completely flawless. Now, there are many languages out there, such as say Java or C# or JavaScript, that are safe. They assume the programmer is a dummy that might make mistakes, right? They check everything. They don't allow you to go over the bounds of an array. Why would you not use these? Well, first of all, it's slower. This has traditionally always been the reason. Programmers like to make a fast program, and users like to have a fast program. So when you write something that's important, you're writing it in a lower level language. Now, this language allows you full control over memory and doesn't do any unnecessary checks. So it's going to be faster than Java, C#, JavaScript, and so on. However, there's also another reason, namely porting effort. Unfortunately, as much as we would like as programmers to always start from scratch, typically almost all programming work works on existing programs or creates programs that have to attach to existing frameworks. In these cases, we barely have any choice of the language we're using. Whatever we used in the past, we need to keep using. And if we do it otherwise, we have a big porting effort in changing all the code already out there to a different language, which is not commercially viable, typically. Finally, we can build a formal proof that the program is safe. So we can use essentially mathematics, which is something computer scientists in theoretical computer science actually do, and we can basically state safety properties and then prove that they're always met. However, this is a lot of work. So it's something that's only viable if we make something that's super critical. So you would probably do this for, say, a pacemaker. It's small, has little code, and it's super critical that it works correctly. However, something like a browser or an operating system, it's just too much work to be viable in the typical case. So there is actually one known case of an operating system that was formally verified, but it does only the bare minimum to keep it small enough to make this viable. Anything else, it starts Linux inside, which is of course not formally verified. Moreover, we can only prove that the system conforms to a specification. So if there's a bug in the specification, it still goes wrong. Okay, so none of these options really solve the problem. What are the realistic options? How can we actually do this? Well, first, try to detect any exploits. So sanitize your input data, including, for example, bound checks. If you make any assumptions on the code, check that those assumptions are met. Now, you can have defenses that can automatically perform these checks in many cases, and it helps prevent a lot of attackers from abusing your code. Another thing we can do, and this is also widely done, is making code execution harder after you exploit something. So if we assume that the attacker is still going to be able to perform an exploit, at least we can try to make sure that they cannot use it in any meaningful way. So an important distinction we can make between types of attacks are local attacks and remote attacks. And we'll discuss both now. In the assignment, we will be focusing primarily on local attacks, which are typically somewhat simpler to do. And they still teach you a lot of important stuff that you would need to do if you wanted to do remote attacks. Now, local attacks use local interactions with the program to manipulate its behavior. So this requires that you already have a presence on the host. And it doesn't necessarily mean that you're actually local in the sense as sitting behind the screen, but you might also have shell access, for example. So if you already have an account to the system and you can access the shell, you can already execute code in there. Another option is that you've already compromised some other application, which now allows you to run code. Right? So you have to be able to run code locally already to do a local attack. Now, what you want to achieve in this case is execute with privileges that the attacker doesn't otherwise have. Right? So you're going to use your ability to execute code to create more privileges that you don't have yet. So these attacks are easier to perform than remote attacks. And the reason is that you have better knowledge of the environment. Right? You can play around with your programs. You can see what happens. You can observe the crashes and so on. So this is in contrast to remote attacks. With remote attacks, we use network-based interactions, and we are not able to execute code remotely. And the strongest type of remote attacks are unauthenticated remote attacks. So in this case, an interaction with the application does not require authentication or any prior capabilities. Now this is the case where we're attacking a simple web server, for example, assuming that there's no authentication to view its pages. Now these attacks are super powerful. They allow us to execute operations with the privilege level of the vulnerable application, even though before we were unable to run any code locally at all. So these are very strong attacks. However, they are more difficult to perform than local attacks because we are often blind. For example, if the system crashes, it may not be reported, or even if the crash is reported, we don't get any detailed information, and we definitely do not get access to a core dump if the system is even remotely normally configured. Of course, you can find cases where stupid configurations make these attacks easier to do. In the general case, remote attacks can be very hard, unless you already have a good idea what kind of software you are attacking.